And of course that 3 was already there, so that 3 just stays there. Okay? And so if this is the function, and we're finding the antiderivative, this is what we do. Add 1, 1 over that number multiplies to whatever's in front. And so this is actually 3 over 6 x to the 6, which is 1/2 x to the 6. And we can double check that by taking the derivative. If I take the derivative of this, I should get this back. So let's just see what happens if you take the derivative. Well, that 6 comes down and multiplies by what's in front. And this 6 here gets subtracted by 1, which gives us 6 over 2, or 3 x to the 5th. And of course that checks out. Yeah, okay. All right, so let's move on to the next one here. Now you might see that we had this n can't equal -1. Okay, so this rule applies right here when n is not equal to -1. Because if n, the exponent, was -1, we would have 1 over x. It's going to be very important to remember that 1 over x was the derivative for the natural logarithm of the absolute value of x, or ln of x. Okay, that's what we just got finished studying last chapter. Excuse me. And so if you see 1 over x, the antiderivative is ln of x. Okay. Also, here's another one here: the e to the power of kx. Now, e to the x. Remember what was really nice about e to the x? It is its own derivative. So the derivative of e to the x is e to the x. So the nice part about that is the antiderivative of e to the x is also e to the x. Right? That makes sense? If it equals itself, then you go backwards, it's going to get back to itself. So that's easy. The tricky part comes when you have this constant here. Like, for example, if we had e to the 3x, if that was our function here, okay, and we wanted to find the antiderivative, well, what you'd have to do then is you would say, yes, okay, it is its own derivative, so therefore it would be its own antiderivative. But when you're taking the derivative, you had to chain rule, you had to multiply by 3, right? So guess what? What's the opposite of multiplying by 3? Really, it's dividing by 3. So to find the antiderivative, you do 1 over 3, or you divide it by 3. So that's where the k comes in there, any constant. And of course, if we checked this, and if we found the derivative of this one, we would have 1/3 e to the 3x times 3. And of course, 3 times 1/3 is 1, and so we get e to the 3x, which is what we get. We get the original back. Okay? Make sense? So instead of doing chain rule, multiplying by the derivative of 3x, we now divide by that constant in front of x. Okay, flipping along here. And then, of course, the two other obvious ones that we're going to take a look at are cos and sine. We know that the derivative of sine is cos, right? The derivative of cos is negative sine. So what happens if we have a positive cos? Well, we're going to go back to positive sine. If we have a positive sine, it's going to come from what would have been a negative cos. Okay? Because, well, we studied this a couple chapters ago. So going backwards, cos, the antiderivative is sine. And of course, if we have a number here, any kind of constant, we do the same thing as we did with the e function here, 1 over. All right, so if we do an example here, and we have, let's say, cos of 2x, okay, and we are using these rules, and we're saying, okay, what's the antiderivative of cos? Well, cos and sine obviously are connected, right? And so it's a bit opposite now. If we were taking the derivative, it would be negative sine, but the antiderivative, we make it positive sine. Okay, and that would be positive sine of 2x, and you'd multiply by 1 over 2. And we can check this by taking the derivative of the antiderivative. And so if we took the derivative of this antiderivative, we should get this back again. And so what does this give us? Well, the derivative of sine is cos. This multiplier is a multiplier. It stays out front. And I multiply the derivative by the derivative of this u function. So that's times 2. And of course, 2 times 1/2 is just 1, and I get cos 2x. So that checks out. Okay? I know this might be a bit tricky the first time through, because you've been thinking derivative for, 3.5 months now, or 3 months anyways, right? So you've been thinking derivative for a long time. So now antiderivative is going backwards. Shouldn't be a big stretch, but you might get a little confused here with, hey, sine and negative cos? That doesn't make sense, Mr. Maxwell. It's supposed to be cos and negative sine. Well, that was with differentiation. So when we're doing the opposite, we've got to think about the opposite sign as well. Okay, so if I give you this function 2x, the question is this always the antiderivative? The answer is yes. If I want the derivative of f of x, this is my notation for the derivative. What is the notation if I want the antiderivative of this? Well, you can't really use this. This means derivative. So the notation is just typically you use sort of the capital version of that letter. Okay, so that's what we're doing for now. So if you have f of x like we normally write it, this is the derivative, and this means the antiderivative. Okay? Good question, though. Yeah. So that's how we notate antiderivative right now. All right. All the rules of differentiation, when we talk about sum and difference anyways, not the power and chain, all that stuff, but sum difference rules, those ones are the same for the antiderivative. So what that means is if you have a function like this, and let's say we have 2x squared minus x plus 7, and I ask you for the antiderivative of x. What you can do is you can simply take a look at each individual term, find the antiderivatives, and either add or subtract as appropriate. So that's what we're going to do. And of course, if I'm looking for the antiderivative, what I'm really meaning is I'm actually meaning the most general antiderivative. So we have to remember to put plus c at the end of every statement, every antiderivative function there. Okay? So plus c, because we're not sure what the constant might have been. All right, so let's go ahead and carry on here. Let's just give myself some room. All right, so 2x squared. Well, if you remember the rules, you take a look at this, and the 2 can stay there. The x can stay there. The 2 as an exponent has to be increased. And then 1/3 has to be multiplied by the coefficient that's already there. So that becomes 2/3 x cubed. We okay with that?
It doesn't matter if we just say 2x cubed or
Okay, so the question is, can you just do this? 2x cubed over 3? What you're going to want to do, it means the same thing, yeah, but you don't want to ever get confused with x cubed over 3, and 2 over 3. You don't ever get confused like that. It's also beneficial, to just write this as a coefficient, because when you're taking derivatives and antiderivatives, the coefficients being separate from the variable as a multiplier it just creates less confusion. So, yeah, you should write this as 2/3 x cubed, okay, as opposed to 2x cubed all over 3. We'll just kind of avoid that if possible. So the next one here, negative x. Okay, so you want to, this is a 1 right now, so we're going to add 1 to that to make it a 2. And then we're going to do this as 1 over 2 x squared. And this is a constant now, okay? This is a constant. If it was 1, the antiderivative would be x. So if it's 7, the antiderivative is 7x. Yes, very good. And then, as we mentioned here, we're looking for the general antiderivative. So we have to remember to put plus c. Capital C, not little c, plus capital C is and you're saying that there may be some constant other than 0 that is part of this antiderivative. We're not given enough information to state that. Okay? How's that?
That was easy.
Yeah, it was easy. Thank you for saying so. Okay. All right, let's do another one. What about this? F of x equals negative 3 e to the power of negative x plus 6 times e to the power of 2x. Ooh, that looks ugly, doesn't it? Okay, I'm just going to give you a minute to work through that and see if you can use your table of antiderivatives there in the book, in the textbook, and yeah, see what you can come up with there. Okay, so there's a look at the worked out solution. Your antiderivative should look like this on the bottom. Don't forget the plus c. So again, it's just the antiderivative is just itself, and then you had a constant here of -1, so divided by -1 here. This again, just itself with a constant of 2, so divide your coefficient by 2 or multiply by 1/2, right? And so you simplify that, and this is what you should get. Let's do another example. Just one more, I guess, before I let you guys kind of on your own to do some real practice here. So let's do a trig function example. Okay, so f of x, let's do this one, equals cos x minus sine x. So if we're looking for the antiderivative, check back to your chart there, and the antiderivative of positive cos x is positive sine x, right? Minus, what's the antiderivative of sine x? Negative cos x. Very good. Now, the u functions here, the inner functions are just x and x, so we don't have to, multiply by 1 over any k value here, so that's kind of handy. Or you can think of it as multiplying by 1 over 1, I guess. Right? You don't need to do that. And, of course, plus c, so the simplified version here would be capital F of x is sine x plus cos x plus c. And there you have it. So the question is, what information would you need to be given if you wanted to actually find out what constant that would be? And I guess what we could do is go back up here to this graph. So let's say that if I wanted to know exactly which graph it was, so let's say this was the graph I had in mind. If this was the function, this was the antiderivative I had in mind, then I would have to tell you that you have an intercept of 2, 0. Or something like that. I would give you a point. Okay? So then you would go, okay, while y equals x squared plus c, I'm given an x value, I'm given a y value, you plug those in, and you solve for c. Both done. So that's the other information there. Now, that'll be. Will it always be a point? I don't know. I can't say always be a point, but some indication, I guess. We can't really can't give you any information about derivative, like, hey, the derivative is 0 at 0, because it's the same for all of these, for example. So a point would be the most likely, the most likely thing that you would be getting here, yeah. Okay, good question there. And then, of course, I'd be asking for the particular antiderivative, not the general antiderivative. The particular antiderivative would have the proper c value here. Okay, and so let's see, for this one it looks like it'd be, 4, 0. So 4 plus what? Because 0 would be, I guess, -4. Right, and so that's where you get -4 there. All right, just to recap the lesson here, an antiderivative is the opposite of a derivative. It's a function, and we notate that by capital F if the original function is small f. It's a function that gives us this when we take its derivative. Okay, so that the derivative of the antiderivative is the function. So it looks like this. For example, 2x has an antiderivative of x squared.